Okay, so this video is to kind of reinforce some of the things we've talked about Le Chatelier's principle and systems at equilibrium by going through a couple of examples. So this is the Haber process example, nitrogen reacting with hydrogen, an iron catalyst producing ammonia molecules. The reaction is said to be exothermic, so delta H is negative, and whenever they tell you that a reaction is a certain type of enthalpy change, whether exo or endothermic, they're referring to the forward reaction. So right away when I see this, I know that the referring to that as exothermic or delta H negative, that's telling me about the forward reaction. So I would say the forward reaction is exo, and I would remind myself that the reverse reaction is endo, because that's going to come in handy if they change the temperature. I'm going to know right away which direction it should shift. So this one says, describe and explain the shift that would result from the following stress on the Haber process at equilibrium. Okay, if more hydrogen is added to the container, that is a way I've essentially increased the hydrogen concentration. Now, ways to think through this. If we think about it from a kinetic standpoint, a reaction rate standpoint, if I increase one of the reactant concentrations, it will increase the frequency of collisions with that reactant, and therefore it'll increase the reaction rate that uses that reactant, that uses that particle. So by increasing the hydrogen concentration, that naturally leads to an increase in the forward reaction rate. That's kind of a collision theory way to think through it. Now, that's often not really the way that's on the equilibrium mark schemes, unfortunately. I wish it was, because I think it's kind of the most intuitive way to think through it. The equilibrium way to think through it is that if I've increased hydrogen, how can the system get rid of that added hydrogen? Because the principle is that whatever I add, the system will will try to remove it, will try to relieve that stress. It doesn't really explain it on a particle level and why it happens. The principle is more about the result, it's more about what happens. So whenever I add something, the system ends up doing something that will lower what I added to get rid of the stress. So that's the shift. So that's kind of the Le Chatelier's principle tells you what will happen. It doesn't do a great job of explaining why it happens, which is why I don't love it, but it will still work in terms of getting to the right answer. So we can also think about it as I've increased the concentration. So how do I remove that added hydrogen? That's the question you need to ask yourself. If you've added something, how do you get rid of it? How do you remove added hydrogen? Well, hydrogen will get used up if I do the forward reaction. So this equals that the forward reaction is favored, is a way to describe that. The forward reaction is favored, and that equals a shift to the right for the position of equilibrium. So the forward reaction is favored, or the position of equilibrium, another lingo term that they will say, shifts to the right. So these are more equilibrium ways to describe what will happen. As a result of increasing the hydrogen concentration, we will favor the forward reaction, which it doesn't mean that the reverse reaction stops. It just means that for a while, the forward reaction will be faster than the reverse reaction. So the forward reaction is favored. And as a result, when I reach a new equilibrium, I will have more of the stuff on the right than I did before. So that's what they mean. The position of equilibrium has shifted to the right, or it will shift to the right. So by shifting to the right, at the new equilibrium that eventually gets reached, you will have less nitrogen concentration. You'll probably have more hydrogen than you did before because it was added. That was the stress. So you'll have more hydrogen. You'll definitely have more ammonia also. So the shift right implies that overall, you're going to have more of the stuff that was on the right when you reach the new equilibrium, and you'll have less of the stuff that was on the left, the reactants, when you reach the new equilibrium. So these are the different types of lingo that they will use in these questions. Instead of saying less and more, they might also refer to it in terms of concentration, probably more likely. So the decrease the concentration of nitrogen by using these brackets, not parentheses, but brackets. That's how I signal concentration. So I decrease nitrogen and I increase ammonia concentration. Different ways to talk about this. We are equilibrium answers. So this is what we're thinking about, is how to remove the hydrogen. It's not really anything that I would write in my mark scheme answer. I just wrote it down to show you what we were thinking about. But by increasing the hydrogen concentration, we should know in the equilibrium topic that will lead to the forward reaction being favored, increase the rate of the forward reaction relative to the reverse reaction. So the position of equilibrium will shift to the right. That really means that at our new equilibrium, I will have more ammonia than I did before, or an increased ammonia concentration. The nitrogen, being the other reactant, will naturally get used up as we make more ammonia, and that's why the nitrogen will go down. Okay, continuing on, if ammonia is removed from the container, that means I've decreased the ammonia concentration. So our question to ourselves is, how do I replace it? Right, so the principle is all about bringing things back into equilibrium. So when you add something, the system will try to remove it to come back into balance, and if you lose something, it will try to replace it to come back into balance. From a kinetic standpoint, decreasing the ammonia will remove ammonia particles, and that equals a slower rate of reverse reaction. Ammonia is involved in the reverse reaction. If I remove a bunch of ammonia, there can't be collisions with ammonia. If there can't be collisions with ammonia, then there can't be a reverse rate of reaction. So it leads to a slower rate of reaction. In terms of equilibrium language, we would say that by removing ammonia, if you think about it in terms of direction, in order to replace ammonia, the forward reaction has to be favored. So for a while, the forward reaction rate, the forward reaction is favored. And that once again is a shift right. Okay, so we slowed the reverse reaction down. Therefore, the forward reaction is faster than the reverse reaction. So we, in equilibrium language, we say the forward reaction is favored, or we say there's been a shift right. And as a result, as the reaction goes to the right, we're going to decrease our nitrogen amount, and we're going to decrease our hydrogen amount. And overall, we're probably going to end up with less ammonia than we had before. But what's really important is that the amounts of reactants will go down because they will be reacting to replace the ammonia. So you have to give up some reactants to make more ammonia. That's what's going on there. So those are some equilibrium answers to that example. Okay, so those were two examples about concentration, both increasing a concentration, so reacting to use it up, or if you decrease the concentration, you will react and shift in such a way that replaces some of what was lost. In the temperature example, all that matters with the temperature examples is that you think about which direction is exo and which direction is endo. A temp increase always, no matter if we're talking physical or chemical, a temp increase always favors the endothermic process, or the endothermic reaction in this case, because it's a chemical reaction, not a physical example. So then we have to look at the example. In this example, we were told it was exothermic, which told us the forward reaction was exothermic. That also tells us the reverse reaction is endothermic. So I know I'm going to favor whichever process is endothermic. So in this reaction, that means the reverse reaction is endothermic. So the reverse reaction is favored. And since the reverse direction is written as pointing to the left, the reverse reaction is favored. We could also say that there's a shift left as a result of the temperature change. So with a temperature increase, we favor endothermic, which means in this example, the reaction is the reverse reaction is favored, and there would be a shift left. But all of these things I'm saying, they are specific to the example we're looking at right here, the Haber process. A different reaction may have an endothermic forward reaction, and therefore a temp increase would favor the forward reaction. So you have to look at each example. So we have a shift left. By shifting left, that means I have increased, so not decreased, but I would have increased N2 and increased H2, and I would have decreased the NH3. In order for the reverse reaction to happen, I need to use up NH3, and I need to make N2 and H2. So when you reach a new equilibrium at this higher temperature, there'll be more reactants in there, and there'll be less product in there. Final example says the pressure is increased by decreasing the container volume. So yeah, that's usually that's one way to increase the pressure of a gas is by, we did this long ago, the gas laws. If we shove the gases into a smaller container, they now have a higher pressure because they collide with the container walls more often. So they may tell you that they've increased the pressure, or they could tell you that they decreased the volume, and you should then know that they've increased the pressure. So if we increase the pressure on a system with gases, always this will lead to favor the process that makes fewer moles of gas, fewer gas particles, because by taking more gas particles and converting them to less gas particles, I end up reducing the pressure, right? So again, it's that same idea of getting rid of the stress. In the temperature example, if I add heat, the system tries to get rid of the heat. It does that by favoring the endothermic process. The endothermic process absorbs the heat. So when you add the heat, by shifting endothermic, we absorb the heat. So once again, we get rid of the stress. That's the Chatelier's principle. In this one, if I increase the pressure, the system will shift to reduce the pressure, and it does that by converting to fewer particles. Fewer particles of gas will mean less pressure. But the general rule is increasing pressure will favor the process where there's fewer moles of gas, fewer particles of gas, but you have to say of gas. You can't just say it goes to the side with less particles. It's the side with less particles of gas. So in this example, there's 4 moles of gas on the reactant side, and there's 2 moles of gas. When those same atoms are arranged as products, they exist as fewer particles. So if we go back to a previous page, you can see that these same 4 molecules are made of 8 atoms, and these 2 molecules are made of the same 8 atoms. So for those 8 atoms, they can either exist as 4 gas molecules or 2 gas molecules. The 2 gas molecules will create less pressure, half as much pressure as if they exist as these 4 separate particles. So the concept is that if you squeeze on them, it naturally causes the reaction that causes them to recombine as fewer gas particles. So in this example, we would have a shift to the right. We'd favor the forward reaction. So that would lead to a decrease in the reactants and an increase in the products. Now, technically, if I had made the volume smaller, probably all the concentrations would go up because concentration is moles per dm cubed, moles per volume. So if I half the volume, I've doubled all the concentrations immediately. So it gets a little bit more complicated. But relative to the concentration when I squeeze them, as they start to shift, we will then lead to a decrease in the reactants and an increase in the product concentrations. Okay? So that's further examples of our stresses and shifts. And let's try one more. Now I've got another chemical equilibrium. I've got the NO2 and I've got N2O4. So this is an equilibrium. NO2 molecules, nitrogen dioxide, are brown. N2O4 molecules are colorless. The equilibrium involves 2 NO2 particles on the left and 1 N2O4 particle on the right. Now I can see they're gas, so this is probably an example where they'll talk about pressure. 2 moles of gas on the left, 1 mole of gas on the right. It doesn't say if it's exo or endothermic, so maybe I'm going to have to figure that out from the question. Okay, the container has an overall brown color due to the presence of NO2. Describe the shifts that occur when the following changes happen. All right, so if I add more NO2, well, it's going to shift to get away from NO2, so it's going to shift to the right. So adding more NO2, we can say shifts will be a shift right, or it favors forward reaction, depends on what they ask. If they say, what's the direction of the shift, you say to the right. Otherwise, you could say either. Therefore, if it shifts right, I bet you added a bunch of brown color, you added more of this NO2, but then over time, the brown color will decrease again as we shift to the right. So when you first add the NO2, you'd make it darker brown, but then the brown color decreases over time as it shifts right. That's the basic premise of what would happen. Okay, if I increase the pressure, it's going to shift to the side with less moles of gas. Well, the right-hand side only has 1 mole of gas. The left-hand side has 2. So increasing pressure will cause it to shift to the right. And so if I shift to the right, again, it should become less brown because I'm making more of the colorless thing and I'm using up more of the brown thing. So it shifts right, becomes less brown. It's shifting to the side with fewer moles of gas. That's what an increase in pressure always does. And since the thing on the right-hand side is colorless, the color should become less brown. Okay, the last one and sort of the trickiest question, it says increasing the temperature causes a new equilibrium to be reached and the container looks like the picture at the right. Determine whether or not it's exo or endothermic. So it would appear that when we increase the temperature, I got more of the brown stuff. So that's more NO2. That's what I was told was brown. Okay, so more brown equals more NO2, which is a reactant. I also know, just as my general rule, that increasing temp favors whichever process is endothermic. So if I look back up here, when I increased the temp, it made more of the left, which means the reverse reaction was happening more. The reverse reaction was favored. It shifted to the left. So that means that the reverse reaction is endothermic. Because it got more brown and more NO2, I know that it shifted left. If the reverse reaction is endothermic, then the forward reaction is exothermic. Just by definition, it has to be that way. So this question wanted to know, is the forward reaction or just the reaction in general exo or endothermic? So I'd say the forward reaction is exothermic. That'd probably be a mark. How do I know that? Because when the temperature was increased, it shifted left, which implies the left process or the reverse process is endothermic. Therefore, the forward reaction must be exothermic. If I go back to one example that's physical, that we didn't really get to talk about. This is a physical example that involves gas. So this side has 1 mole of gas, this side has no moles of gas. So this can also be affected by pressure on the left and 0 moles gas on the right. If I increase the pressure, it favors the side with less moles of gas. Well, which side has less moles of gas? The side that has 0 moles of gas on it. So that's why when we increase the pressure of gas, it pushes more gas into the solution, dissolved in the solution. So at high pressures, more carbon dioxide can be dissolved in water. So you get a lot of CO2 in the water. Notice when you have a soda bottle closed, you don't see bubbles in it. All the CO2 is in the solution, dissolved in there like sugar or salt dissolved in water. When you take the cap off, you very quickly drop the pressure. So when you decrease the pressure, that shifts to the side with more moles of gas, which is the left. So carbon dioxide that was dissolved turns back into gas. So you see bubbles. So that's why when you open a soda, or any carbonated beverage, right, you immediately see a bunch of bubbles form out of the solution. Where did those come from? They were all dissolved. So this picture is a little bit misleading. You actually wouldn't see any of those bubbles. It's trying to indicate that they're dissolved, but when they're dissolved, you don't actually see them. As soon as you uncap the bottle and you decrease the pressure, a decrease in pressure shifts to the side with more moles of gas. In this case, that's left. And what that means is the carbon dioxide that was dissolved is now turning back into a gas and it comes out as bubbles. And that explains why you see bubbles when you drop the pressure on a carbonated beverage.